Good morning everyone. Today I will present the paper, A Supervised Multitask Framework for Joint Cryo-ET Restoration Enabled by Generative Physical Simulation. The proposed method is called cryoDeRec. It focuses on two major degradation problems in cryo-electron tomography reconstruction, low signal-to-noise ratio, and the missing wedge caused by limited angle acquisition. The main goal of this work is not only to denoise cryo-ET tomograms, nor only to recover the missing wedge. Instead, it aims to perform joint cryo-ET restoration in a unified framework. First, let me introduce the background. Cryo-ET enables in situ observation of cellular ultrastructure under near-native conditions. It is an important tool for studying viruses, proteins, and organelles. However, cryo-ET reconstruction quality is limited by two major factors. First, the electron dose must be kept low to avoid radiation damage. As a result, the projection images in the tilt series usually have low contrast and extremely low signal-to-noise ratio. Second, the tilt range is usually limited to about plus or minus 60 degrees, rather than a full 90 degrees. This leads to an unsampled region in Fourier space, which is known as the missing wedge. These two problems jointly cause structural blur, elongation artifacts, and reduced interpretability. Therefore, the core question is, how can we simultaneously achieve denoising and missing wedge recovery to improve cryo-ET reconstruction quality? Existing approaches can be roughly divided into three categories. The first category is denoising-only methods, such as topaz denoise and SCNet. These methods can suppress noise, but they cannot effectively restore the missing wedge. The second category is missing wedge recovery-only methods, such as ISONet. These methods can recover part of the missing information, but they are sensitive to input noise. The third category is joint restoration methods, such as deep to wedge. However, existing joint methods are mostly self-supervised and still lack reliable clean ground truth support. The core limitations are clear. First, true clean or complete tomograms are nearly impossible to obtain experimentally, which makes conventional supervised learning difficult to apply directly. Second, denoising and missing wedge recovery are strongly coupled. Noise can interfere with reconstruction, while structural artifacts can mislead denoising. Third, many existing methods process the two degradations separately, leading to incomplete restoration and limited generalization. So the research gap is, we need a joint framework that can construct reliable training data and jointly optimize denoising and missing wedge recovery. This slide shows the overall framework of cryoDeRec. The key idea is to use generative physical simulation to build high-fidelity simulated training data, and then train a multitask restoration network. The method contains four main modules. The first module is noise modeling. The authors extract noise maps from movie frames and motion-corrected projections, and then use WGNGP to learn complex noise distributions. This is important because the noise in real cryo-ET is much more complex than simple Gaussian noise. The second module is structure density and sample synthesis. The authors select macromolecular structures such as HIV, ribosome, and nucleosome from EMDB, and combine them with the SAWLC distribution to generate diverse 3D structural scenes. The third module is imaging physics simulation. It incorporates CTF modulation, limited angle projection, and WBP reconstruction. Through this process, the framework can generate noisy tomograms as inputs and clean tomograms as training targets. The fourth module is the multitask framework. It optimizes two losses, fidelity loss, which restores overall structural fidelity, and reconstruction loss, which restores missing information. The key advantage is that cryoDeRec transforms the problem of unavailable true ground truth into a controllable, high-fidelity supervised learning problem. This slide shows the experimental results. We evaluate cryoDeRec on both real and simulated datasets. On the left, we can see results on real Ampere datasets, including Ampere 10045, ampere 10049, ampere 10678, and ampere 10643. Compared with WBP, Topaz Denoise, SCNet, and ISONet, cryoDeRec produces clearer structures, stronger contrast, and fewer artifacts. On the right, the results are shown on simulated datasets, where ground truth is available. In both Fourier space and reconstructed slices, cryoDeRec shows better missing wedge completion and more accurate spatial reconstruction. The main conclusion from this slide is that cryoDeRec consistently outperforms existing methods in joint denoising and missing wedge restoration. It is also worth noting that the model is trained using simulated data, but it can still generalize to real tomograms. This shows that the simulated supervision is effective. This slide presents the ablation studies, which explain why the method works. First, the role of reconstruction loss is important. Without reconstruction loss, denoising is noticeably weaker and artifacts remain. With the full loss, the model achieves the best denoising performance and better artifact mitigation. Second, the authors study the effect of the noise model. They compare WGNGP noise modeling with Gaussian noise at different SNR levels. The results show that simple Gaussian noise cannot accurately represent real cryo-ET noise, while WGNGP provides more realistic noise modeling and leads to better restoration quality. Third, the authors analyze parameter sensitivity, especially the weight lambda_recon. The results show that lambda_recon equals 0.1 provides a good balance between noise suppression and missing wedge recovery. Overall, the ablation studies validate the effectiveness of reconstruction loss, realistic noise modeling, and proper parameter choices. To conclude, this paper proposes cryoDeRec, a supervised multitask framework for joint cryo-ET restoration. The main innovation is the combination of generative physical simulation and fully supervised multitask joint restoration. In terms of performance, cryoDeRec simultaneously improves denoising and missing wedge restoration, and shows good results on both simulated and real datasets. The ablation studies further confirm that realistic simulation-based supervision, WGNGP noise modeling, and a multitask loss are all important for improving restoration performance. However, there is still a limitation. The current training process requires structure-specific simulated training data. Therefore, separate models may be needed for different real datasets, which limits the generalizability of the method. That is all for my presentation. Thank you.